Hey guys, just starting our Force to Accelerate virtual lab. These are the materials you need to have right now, so we can pause if we need to, but you need to have your science book. We're looking at the lab on page 50 and 51. You'll see there's an assignment in Google Classroom for this, which is where you will find your Force to Accelerate data table. I'm going to show you what that looks like in just a second. Part of this lab is also graphing with pencil and paper. So you will need a piece of paper and a pencil unless you know how to graph with a computer program, and then you're welcome to write a graph that way. So these are the things you will need. All the other materials we will provide here and show you in the virtual lab. I'm coming to you from the high school lab, and we have Mr. Henson here helping us. So we're going to do all of the data collection and teach you how to do that. And then you're going to copy it down in the data table, and we'll do the averaging and the other calculations together as a class. So first things first, you need your textbook, page 50 and 51. This is the teacher version, but it's the Force to Accelerate lab. This is what it looks like with these images, page 50 and 51. So the first thing we do when we start a lab is make sure that we have all the materials that we need. And so for this lab, we need to have a skateboard. Mr. Henson's going to bring those in. A skateboard, a string, several bricks or other large masses. We didn't have bricks, but we have these ball bearings that we put in a Skippy jar so that it doesn't spill. We need a meter stick, which we've actually already set up, and I'll tell you what exactly we did with that. And then we also need a spring scale, which we're measuring force with. The rate of measurement, the scale of measurement, scale of measurement that we're using is newtons. So when you see in your unit, there we go, yep. The unit of measurement that we're using is newtons. And so that's what the scale measures. Mr. Henson is going to show that closely. And then we'll talk about how to make sure that that scale is zeroed when we start. We want to make sure that anytime we're measuring, it starts from 0. So on that particular scale, it has a dial that we make sure it starts at 0. Anytime we measure something with the scale, we want to make sure that it's 0. That's the same if you're measuring or weighing something for cooking or using any other sort of scale. And then we also, for this lab, we're going to need a stopwatch. So since we're in the lab, we have a real stopwatch. And we'll be using that as we measure the time that it takes for the skateboard to travel with the weight. Okay. So what we're trying to figure out in this lab is how the acceleration of a skateboard is related to the force that is pulling it. So this is similar to some of the other labs we've done, talking about speed and distance, but now we're talking about force and acceleration. So we're seeing how much the skateboard accelerates and how that changes based on how much force we're applying. Anything to add to that, Mr. Hinton?
No, that's perfect.
Okay. So what I want you to do is we're going to look through the procedures, and I want to do this very specifically since you don't have this stuff with you, but I want to talk you through the process of what you would do if you were setting up this lab on your own. So we're looking at the procedure part on page 50. Number 1, the first part is to attach a string with a loop to the skateboard. So what we've done is we've attached the string to the skateboard, and then there's a loop on the end that Mr. Henson is holding so that we can hook that loop onto the scale. Thank you. And so we'll be able to measure. Show us how that works, Mr. Henson. If we hook it on, how does this work? Can you explain that when you're pulling it?
So
what that shows?
So it shows a force. So the harder that you actually pull, the more force you're going to apply. So if we pull slightly, it's going to move, right? If we pull harder, the more force is applied, it moves faster.
Perfect. Okay. So we've got our skateboard, we've got the string attached with the loop. The next piece is that marking a specific distance. So that's what the meter stick is for. So we've taped it on the side of the counter here so you can see exactly how far a meter is. The instructions say to put a piece of tape at the start and a piece of tape at the finish. So we're going to be starting from this line here and ending when it touches the tape on the other side. So we're looking at the wheels specifically, just for our own measurements. We're saying as soon as the wheels cross this line, I will start the time. And as soon as the wheels touch the beginning of the line on that end will stop the time. So we're making sure that we use the same plan each time we measure time, the exact same distance. Okay, so we've attached the spring scale with a loop on the string, and the instructions say to pull it so you can maintain a force of 2 newtons. So Mr. Henson is going to model how you would do that. And we also have this weight. I don't think we talked about the weight. The weight is just to make sure that we have enough mass to actually do this experiment.
So if I pull 2 newtons, before I get there, it starts moving.
Yep.
So if I hold it still though, I can pull and just feel what 2 newtons feels like. Right there, the dial is pointed right at 2. It kind of moves up and down a little bit because I'm not perfect, I am human. So that's what we have.
Yep. So one of the reasons we do so many measurements, as you can see when you look at the data table, we're going to do 3 trials of each amount of force when we pull the skateboard. There are lots of areas in physical science where there's room for human error. And so this is one of them, because we as humans are trying to pull on this and maintain a force of 2 newtons, which is really hard because this wants to move. So we do 3 trials and then we average the times so that we can try and get as accurate of a reading as possible by still researching with a margin for human error. So now that we have this set up, basically what Mr. Henson is doing is practicing pulling it at 2 newtons so we can practice getting what, Mr. Henson? A constant
Velocity?
Yes. So what we want to do each time is be able to pull it with a constant force, right?
Yeah, so we want to try and find out, we want to balance the forces here and get it to move at a constant speed, right? And so we want to see how much force does it actually take to get it to just to move, not to accelerate, just to move and move at a constant speed. We don't want anything more than just movement, because we want to balance the forces, right? Because we've got a force I'm pulling this way, but if it's at a constant speed, there's something else happening that's keeping it from accelerating. So the force that we're seeing here is friction, the friction of the ball bearings, the friction of the wheels on the ground. And so we're trying to balance those so we know exactly how much force it takes to move this at a constant speed.
Yep. So in step number 5 of the experiment, the job is to find that smallest force needed in order to, sorry, my computer just did something crazy. We're good. In step number 5, it says find the smallest force needed to pull the skateboard at a slow, constant speed. Do not accelerate the skateboard. So what we have here is a constant speed. We're not accelerating because we have the same speed and the same amount of force pulling on it. So what we found is that it takes about 1.5 newtons of force to be able to keep the skateboard going at a constant speed. So, and that's what they're asking in step number 5, is to find the smallest force needed to pull the skateboard at a slow, constant speed. So this is just enough force to get it moving and keep it moving is 1.5 newtons. We've tested it multiple times before we started also, and we both came up with that same answer. So what we're going to do now is we're going to be referencing your data table. So really quick, I'm going to pull it up and show you what that looks like. You guys should already have it pulled up, but I'm going to also show it right here. So what we have right here is the force that we're going to be pulling the skateboard with. And then we're going to do 3 trials of time to see how long it takes to get from start to finish with that amount of force being applied. So if we look at step 6, it says add 0.5 newtons to the force in step 5. So if all of this feels confusing, make sure you're following along in your book so you can kind of see what the overall plan is and reference back and forth. So step 5 was to find the smallest force, which is what we just did. Step 6 is to add 0.5 newtons to the force in step 5. So Mr. Henson and I both agreed it was 1.5 newtons. That was the smallest force to be able to keep the skateboard moving at a slow, constant speed. So if we add 0.5 to 1.5, we know that we're starting our first trial with a force of 2 newtons. So in your data table, make sure that you write 2 right there. And then what we're going to do is we're going to do 3 times. We're going to go start to finish, and we're going to time each one. So the first time we do it, in trial time 1, you're going to write down the amount of time it takes to get that distance. And then we're going to do it 2 more times. And those are those 3 columns that I just clicked and highlighted. Those are the 3 that we're filling out right now. We're going to leave all the average time and average speed, that all of those columns we're going to talk about after we collect our data. Okay? So this is the area that you're going to be looking to fill in. I'm going to make this bigger so that you can see us. Hopefully that works. What we're going to do is that Mr. Henson is going to pull this scale so that he has a force of 2. I'm going to hold this. Let me get my stopwatch. I'm going to hold this. And then he's going to get it to a force of 2. And then he's going to tell me to go. And I'm going to measure I'm going to start my time here when it starts. And I'm going to end my time there right as soon as it touches the finish line. So we're going to try and find how long it takes for this skateboard to travel that distance with a force of 2 newtons pulling it. So.
All right, ready? And go.
Oh, I did it wrong. That's the human error. Let's start again.
We can try again.
And you'll see how the scale bounces. And that's part of the human error piece. We've been practicing this a lot, and it's really hard to make it always not bounce. So we're just going to keep doing it. And then let me get it where it goes. I am ready. Oh, no, I'm not. There we go. Now I'm ready.
Ready? And go.
Perfect. Okay, so I have my computer. I'm pulling up my data table. And that first trial time, I'm looking up and seeing what it was, and it was 3.84. So what you're going to do on your sheet is type in this first trial time, 3.84 seconds.
Always use units.
Correct. The units are actually up here, but just so that is a very good point to make sure that you know what this. So we're with a force of 2 newtons. We traveled 3.84, or we traveled that 1 meter distance in 3.84 seconds. So we're going to do the same thing. I'm going to read off the times, and you're going to write down how much time it takes the second time, and then again when we do the third time. So and then I'll make sure and go and show you also. Okay, so we are about to do it one more time. Let me reset my stopwatch.
I'll try to be as consistent as I can, but it is definitely fluctuating. So I'm going to try to get the average about 2.
Yeah.
All right, ready?
Mm-hmm.
And go.
All right, so that one was 3.5. So we're going to go back to our sheet. That trial time was 3.5 seconds. Okay, that's what it should look like. We're going to go and do the third trial really quick, and you're going to write down the amount of time right here.
Okay, 2 newtons, third trial.
Okay.
And go.
All right, that third time was 3.78 seconds. So we're going to put that on our sheet. What did I just say? I have it written down over here too.
3.7, or sorry, 3.71.
78.
3.78.
3.78. There we go. That's what it's going to look like. Okay, so we're going to do the same thing over and I'm not going to keep coming back to this sheet. I'll show you at the end what it should look like. But basically the next step in the experiment is to do the same thing. Where is it? On number 11. So on page 50, go to number 11, and we're repeating all those steps we just did to measure. We're repeating that using a force that is 1 newton greater than the original force we found that just barely moves it across. So the next force we're going to be using is 2.5. And just for your own ease, we're going to do this we're going to go through and do it with 2.5 and do 3 trials. And then we're going to go through again and do it with a force of 3 newtons and do 3 trials. So we're going to only do those 2 amounts of force. So first we're going to do 2.5, and I'm going to have you guys record your data. So as we pulled in trial time 1 with a force of 2.5, I'll let you write down what we find, but we're just going to go through and do 3 trials with 2.5, and then we're going to do 3 trials with 3 newtons, just so you can quickly see that, and you should be recording your data, and then we'll confirm that you have the correct answers. Okay.
All right.
All right, so what's the force we're doing right now?
2.5 newtons, trial number 1, pulling the 2.5 and release.
All right, so 2.5, the first trial one time for 2.5 is 2.22 seconds.
Trial number 2 at 2.5 newtons and release.
Okay, trial number 2 of 2.5 newtons is 2.25 seconds.
All right. Trial number 3, 2.5 newtons and release.
Okay, trial number 3 is 2.56 seconds. So you should have filled out your sheet for trials 1, 2, and 3 for pulling at 2.5 newtons. We're going to do the same thing for 3 newtons, and then we're going to move on, and I'll show you what it looks like.
All right.
Okay, so we're doing a force of 3 newtons, and this is trial time 1.
Trial 1, 3 newtons and release.
All right, trial time 1 is 1.97 seconds.
All right. Trial 2, 3 newtons and release.
Trial time 2 is 1.75 seconds.
Trial 3 at 3 newtons and release.
Trial 3 is 1.78. So I'm going to add this data to the main sheet and then show it to you. I have it written down here. Give me 1 second. Oops. And what I'm doing is updating the sheet that I have on this computer. So I'm going to show you what the times are, just in case you didn't get them written down. Okay, so this is what your force to accelerate data table should look like. So we tried pulling the skateboard with the weight 3 different times using 3 different forces. The first time at 2 forces, these were the 3 different trial times. The second time with 2.5 newtons of force, we did 3 trials and those were the times. And then the third time we did 3 different trials and these were the times that we got those 3 times. So at this point, I'm going to pause this video, and as a class, we're going to go through and find average time, average speed, and the final speed and acceleration, those other pieces of this board. So I will pause, and we will come back to this for Mr. Henson to go through the graphing piece with you. Just a second.
All right, so now we're looking at graphing what we just took measurements of and the calculations that you did to find acceleration. So we are graphing a plot of what we're asked to do of force and acceleration. So if you look at what you guys came up with, we had a force initially of 1.5 newtons, then we did 2 newtons, we did 2.5 newtons, and we did 3 newtons. And what was the acceleration corresponding to those? We start with the 1.5 newtons, which we'll draw a quick coordinate system. This is what I want you to draw on your paper. There's a Y and then an X plot. We are going to add on our hold on one second. My computer thinks I'm talking to it. So it's asking us in the book to have acceleration be on the y-axis and our force to be on the x-axis. We're going to go from 0 here to 1 meters per second squared for acceleration. We can break that down a little bit smaller to 0.5, and then right in between here is 0.25, and then we'll do 0.75. So just breaking it down into quarters. Force, we're going to go from 1 to 3 newtons, right where we were. So we can break this one down to 1. One second, be a little more accurate with that. Break this down into 1, 2, and 3 newtons meters per second squared. Never want to forget units. So there's our Cartesian coordinates that we're going to be graphing on. And we have our information here. So we have 1.5 newtons. Our acceleration at that point was 0. How do we know that? Because we balanced the forces. Remember, we had our skateboard here, and we were pulling with our force this way, and then there's something pulling back, right? Friction. So the force of friction was pulling back. We balanced the forces, making sure that we had 0 acceleration. So we know that 1.5, so we count out here 1, and then halfway between 1 and 2 is 1.5, and we're going to put our first point. Then for 2 newtons, we came up with an acceleration that we calculated in class of 0.15 meters per second squared. So for 2 newtons, we got 2 newtons. We're going to move up to 0.15. Now, here's 0.25, 0.15, just a little bit below that. Okay, there's our graphing point for the second one. Now, 2.5 newtons, we calculated 0.37 meters per second squared. So we're going to count up 2.5 newtons, 1, 2, halfway between 2 and 3 is 2.5. We're going to go up to 0.37, which is somewhere right in between 0.25 and 0.5. So right about there. Perfect. All right. 3 newtons. We're going to go 3 newtons. Our acceleration we calculated was 0.60 meters per second squared. So let's go up to 3 newtons, 1, 2, 3, and then we need to go up to 0.6. But here's 0.5, 0.6 is just a little bit above that, right there. There we go. All right, there's our plot. We plotted all of our points. And the next step says, if your data points seem to form a straight line, draw a line through them. So we can go ahead and draw a line right through them, starting here and moving. Oh, look, that's pretty darn straight. There we go. The next step, your first data point is the force squared, you accelerated 0. We already talked about how do we know that the acceleration is 0 because we had a constant speed. And according to the graph, how is the acceleration of the skateboard related to pulling force? So the acceleration seems to go up at a constant amount for every constant amount of force that we apply. So they are, this is called a linear scale. The more force applied, the more acceleration goes up, and we can predict that. So what variable is the manipulated variable here? What did we manipulate? We manipulated our force, right? We changed it, and we varied it, and we tested with different amounts of force. And so which variable is the responding variable? That's our acceleration. Our acceleration responded to our changes that we did in force. And this is how we get on the x-axis. Force is what we changed, and then we graphed what was responding to that change. Thank you all for listening to me on this, and I will see you all later. Bye.